Hello and good morning. Welcome everyone to
Good morning.
inaugural lecture of the IMSc Distinguished Lecture Series as part of the 75th year of India's independence. We are extremely happy to have Professor R Chidambaram deliver the inaugural address. I would like to call upon our director, Professor Ravindran, to kindly introduce the speaker.
Yeah, am I audible now?
Yes.
Okay. Thank you, Professor Vishwanath, for organizing this. It is indeed a great pleasure to have Professor Chidambaram with us to deliver this distinguished lecture in the lecture series to commemorate 75 years of independence. Okay, and I would like to invite him for this distinguished lecture. This is the first lecture in this series. And would also like to say a few words about his achievements. And of course, it is known to most of us. And for the younger audience, Professor Chidambaram is currently holding DAE Homi Bhabha Chair, Professor. And between 2002 to 2018, he was Principal Scientific Advisor to Government of India and Chairman of Scientific Advisory to the Cabinet of Federal Government. Before that, he was Chairman of Atomic Energy Commission and Secretary of Department of Atomic Energy, and IMSc is part of it actually. Before that, from 1990 to 93, he was Director of BARC, Baba Atomic Research Center. These capacities he has been, he was a key architect of Indian science policy for several decades, actually. So he's one of the, policy makers of Indian science. And we should be proud of Dr. Chidambaram because he is from our city. He did his BSc and MSc in physics in our city. So we are very proud of having him here as a first lecture, eminent speaker for this series. And it is PhD after, at Indian Institute of Science. And he also won Best Thesis Award. It's called Martin Foster Medal in IISc, and he was a PhD student after he completed. He had carried out its research in India, most of the research in India, published more than 200 research papers, and all of them appeared in refereed international journals. He has made contributions to diverse areas, including nuclear physics, crystallography, condensed matter physics, material science, high pressure physics, among others. And he was not only a great academician and administrator, he was also key to member of the testing team of, famous Pokhran 1 in 1974 and Pokhran 2 in 1998. He won several awards. He was a recipient of numerous awards and honors that include, I'll list few of them, the Padma Vibhushan, Padma Shri from Government of India. He's also fellow of science academies in India, almost all academies of academies in India, and also he is also fellow of the World Academy of Sciences, TWAS, Trieste, Italy. So I'll not take too much time on this, and I'll request Professor Valstronium to say a few words because Professor Valstronium had a close association with him for a very long time, and I will hand over to Professor Vishwanath. I would like to welcome again and thank you for.
Thank you, Professor Ravindran. I call upon our former director, Professor Valstronium, to please say a few words.
Thank you very much for the invitation. Am I audible?
Yes.
Yes. Okay. Fine. About the academic achievements and the administrative positions which Dr. Chidambaram had, I think Ravindran has already explained. And therefore, I would probably talk about a little about the personal touch. And the time when I became the director, 2000, Dr. Chidambaram was the chairman DAE. But his tenure was there only for, after that, only for some 6 or 7 months, if I remember correct. and consequently, I did not have much occasion to interact with him. But then later, when he became PSA and the sets came under his control, and he wanted me to take part in the activities of the sets, which I did. And it is in this connection that I have had a lot of interactions with him. And that's the time when the sets, we were trying to restructure the organization, going from the PPT mode to the other mode. And that way, then we had to work a little hard, and I could clearly see how much meticulously he is planning the things, and and how successfully he was able to bring that out. And one personal thing which I would like to say, that there was a certain time when I had got into certain trouble, and if I could not resolve it within a couple of hours, etc., it would have led to certain embarrassment. And I didn't know what to do until then I called Dr. Chidambaram. And Dr. Chidambaram, if I remember correct, at that time was in Tanjavur for his personal work. But even then he heard it and he immediately took action. And within 10 minutes, he got the problem solved. And this is something which I would never forget, because if I could not have solved the problem, what embarrassment I would have gone through. And I am deeply ever indebted to him for that. And later I had an opportunity to work in a committee under his chairmanship regarding the financial aspects of the aided institutes. And again, where I could see clearly how meticulously he was able to plan the things and how meticulously finally the report came, etc. And I am very happy that the first lecture of this Amrit Mahotsava is given by Dr. Chidambaram in IMSc. Thank you.
Thank you, Professor Valstronium, for those nice anecdotes. So, without further ado, I call upon Dr. Chidambaram to please give your address.
Thank you, Dr. Vishwanath. I'm also very grateful to the introduction by Dr. Ravindran and my friend Dr. Balasubramaniam, friend for a long time. And it's a pleasure to give this talk. Of course, the statement that mathematics is used widely in physical sciences is a no-brainer. It's so obvious. I think I'll start my PowerPoint presentation. Thank you. That is very obvious that mathematics is widely used in physical sciences. In fact, there is a famous quotation by Roger Bacon, the 13th century, which says mathematics is the door and the key to the sciences. This is in this dictionary of scientific quotations by my friend Alan McKay, who gave it to me. Go to next slide. See, if you take the division of scientific disciplines, physical sciences contains physics, chemistry, material science, astronomy, and so on. And of course, today, I would like to add some of the engineering disciplines, mechanical, electrical, electronic, and computer science. Some IITs where they are giving courses in engineering physics. The dictionary definition of mathematics is a group of related sciences into algebra, geometry, and calculus. And they concern the study of number, quantity, shape, and space. Actually, in common parlance, usually only those working in pure mathematics seem to be called mathematicians. Otherwise, they are called theoretical physicists, theoretical chemists, and so on. Of course, there are applied mathematicians and other fields like engineering, computer science, and even biology, finance, and business. Many of the fields are covered in the research programs of IMSc, which I show you in the next slide. Go to next slide. Theoretical physics, astrophysics, cosmology, fluid mechanics, machine learning and artificial intelligence, quantum information, particle physics, complex systems, and so on. Mathematics, IMSc, algebra, representation theory, algebraic geometry, number theory, in which we have always been strong, theoretical computer science, both algorithms and other things like computational complexity, and computational biology, modeling of infectious diseases, and neuroscience. Next slide. See, high energy physics is an important area where the highest level mathematics is used. In classical mechanics, the entire thing is captured by a small set of variables. And we study the dynamics by looking at the time evolution of these variables. Quantum mechanics, the classical variables are turned into operators and encoded into a wave function. And this standard model particle physics is really a gauge quantum field theory. And then we have string theory, in which the point-like particles of particle physics are replaced by one-dimensional objects called strings. See, normally after the general theory of relativity, people have got accustomed to 4 dimensions, space and time. But string theory involves 10 dimensions. And it's very difficult to conceive, to visualize on the basis of everyday experience when you begin to describe every point particle by a string, by one-dimensional object. And there is a Hoover string theory, which probably, M theory, which probably has 11 dimensions. Next slide. See, this high energy physics I talked to you about, talked of the standard model. It has got all the particles we come across with. It also predicted by the Higgs boson, Higgs field boson, and they had said that it's a mass of 130, 150 times the mass of the proton, and this could be seen only when the Large Hadron Collider came up. When two particles collide, energy disappears and particles can be produced. And higher the energy of the colliding particles, higher is the possible mass of the new particle that you can produce. And they knew that unless they go to 4 tera electron volt collision of hadrons or protons, they will not be able to see it, but they did when in this experiment some years back. And it's, as many of you know, it's 26-kilometer circumference tunnel in Geneva, 100 meters below the ground, where protons are moving in opposite directions. They're bent by dipole magnets, but when they have to be, the orbit has to be corrected, you have to go to superconducting corrector magnets, sextupole, octupole, and decapole. And 1,800 of them, costing, in, according to their estimate, $40 million, was supplied by the Department of Atomic Energy through RRCAT Indore. And of course, the experiments, CMS, TFR is involved, Alice, WEC, and CMS actually saw the track, what you see over here, CMS model, the Higgs boson. The signature of the Higgs boson was seen in the CMS detector, and the data came directly to TFR and other collaborating institutions, because we now have the National Knowledge Network, which connects all the leading research institutions and universities and national labs in India. Of course, we also participate in ITER, so thermonuclear experimental reactor project in Kadrash. And of course, here again, we are supplying some critical equipment to this international consortium, which is building this ITER in France. Next one. See, there are more than, LHC is one of the biggest accelerators, LHC, Large Hadron Collider. But there are more than 30,000 accelerators around, big and small. And if you look at the basic equation governing motion of charged particles, as you look at the equation is given here, kind of mathematical techniques. They are integral. These techniques are integral part of the design of the accelerator. Normal magnets, RF structures, charged particle beam dynamics, focusing, transport, and so on. This slide is by Dr. Kailas, who is a leading nuclear physicist. Next slide. Of course, we also build synchrotron radiation sources, which become a very common facility, very valuable. Produces beams 1,000 times and more in intensity compared to what you get from a laboratory X-ray source. And also you can vary the wavelength, because normally in the laboratory X-ray source you get K alpha X-rays. And it is being very, very widely used, put in beam lines. And you can, next slide shows how, next slide. If you want to predict something, it has to be experimentally vindicated. And this was done, this slide by my colleague Dr. S.M. Sharma from our high pressure physics group. See, they use the technique of molecular dynamics to look at the movements of atoms and molecules. And they look at numerical step-by-step solutions of the classical equations of motion. About this Nobel Prize work, and solving the structure, starting with solving the phase problem, as I was telling you, to least squares the refinement of the structure, and so many other factors, we have to use mathematics. And in fact, artificial intelligence has also started being used here, because they take pieces of the amino acid sequence, similar in several proteins, patch it together, and there are more advanced methods coming from Google, like the AI Mind and all that. Next slide. See, mathematical modeling for any pandemic, mathematical models can be employed to study the disease dynamics. That is the disease spreading, in which I notice IMSc has interest, and develop prevention strategies against the spreading. And the influential parameters are identified first, and then the proper prevention strategies, for example, lockdowns, are developed. Of course, lockdowns can be done even without any modeling. And such modeling has been done for COVID-19 pandemic in India and other countries, several labs. And these models also attempt to predict when this epidemic will peak out, and also to speculate whether there would be a next wave, if so, when. Next. And this is where this use of computers have gone up, particularly second half of the 20th century. As we started getting computers of ever increasing power, or what is, then it became almost, it's called computational science. That is investigations in which advanced computing capabilities are used to understand and solve complex problems. The physical and biological science. Of course, you can get addicted to it. I'm told there are some people who differentiate science, including a computer. The essence of computational science, the development of algorithms based on mathematical models and their use in simulation. Mathematics, of course, is the foundation on which computer science is built. But computing is also increasingly used as a key component in mathematical problem solving. And there is a term they use for it, it's called computational mathematics. Next. Because there is a supercomputing mission in India. Most scientists have access now, which was not there a couple of decades back, or even a decade back, supercomputers. But indigenous development of supercomputers, the leading lab is BRC, and this Anupam supercomputer series, and Anupam Atulya, for example, is giving a peak performance of 2 petaflops. 2 petaflops, gigaflops, teraflops, and then petaflops. Next one. See, this is the indigenous 3-stage program. And as you, most of you know, PHWRs, heavy water reactor in the first stage, Kalpakam, used to take the plutonium from that and build plutonium fuel fast breeders, and then expose thorium there, convert to uranium-233, and then go to the thorium-232, uranium-233 cycle, which will be the third and last stage of our program. This was developed from the time of Homi Bhabha, because we don't have enough resources of uranium. But fortunately now we are able to access global uranium after the change of the nuclear supplier group guideline. Addition to that, in order to add to our nuclear power capacity, we are also bringing in light water reactors with international cooperation, like the one in Kudankulam. Next slide, please. See, if the very high level of mathematics is used in optimizing the nuclear reactor design. I don't want to go into the details. You have the transport equation, and then which has to be solved, taking into account all these parameters. And then you have to divide the energy domain into many different energy groups, and then put boundary conditions and so on. And all this, you have the safety of the reactor in the mind all the time. Next slide. This was given to me by Dr. Uma Shankari Kannan, who heads the reactor physics group. So you use in the determination of the neutron flux both the stochastic approach, and which is non-deterministic, and also the deterministic approach. I just want to give you a feeling for the kind of mathematics that is being used in all these applications. Next slide. See, take fusion energy, which is the probably come in the future, and the biggest fusion thermonuclear experimental reactor is being built in Kadrash, is international effort. 8 countries are involved, and India is one of them. We are a major supplier of equipment for this reactor. This is magnetic confinement fusion using the Russian method, which is called the tokamak. It's a donut-shaped instrument. But the temperatures you are trying to reach are 50, 100 million degrees. No material can hold it. So you have to hold it by a complex interplay of magnetic fields, which requires a great deal of mathematics. And here, what you are seeing, the entire tokamak has to be housed inside a cryostat. And this cryostat, which is the largest vessel of its kind in the world, with the ultra-high vacuum-compatible vessel, 30 meters in height and 30 meters in width. The base of this, built in India by L&T, Azira, under the supervision of the Institute of Plasma Research, has been installed in Kadrash early last year. Of course, fusion science is a theoretical physicist's delight. It was fascinating to look at the whole thing. But fusion technology is a huge challenge. This is what I said in my inaugural address in the 27th IAEA Fusion Energy Conference. Well, this is the tokamak, which is the most popular magnetic confinement fusion at the moment, device at the moment. But there are others like Stellarata, which is being promoted by Princeton University. But there the geometry is more complex. And getting this complex magnetic field structures there is much more complex. And then, of course, you have the inertial confinement fusion, and there's the National Ignition Facility in Livermore, which is for this in the US, where a large number of beams come and hit a small pellet and make it implode like you do in a nuclear device, weapon device, and then the temperature goes up to fusion temperatures. Next slide. Mathematics, I must tell you, is used by all these high-tech organizations. The launch vehicle trajectory design involves mathematics. And of course, we are ISRO, we are proud of ISRO's accomplishments, manned flight mission. And Chandrayaan 2, which is a wonderful project. Of course, the rover didn't work, but the satellite which is put around the moon, that is sending them continuously good data from there. Next slide. Same thing with light combat aircraft, which has been introduced, Tejas, which has been introduced in the Indian Air Force, designed by DRDO. It's actually a flagship program for Make in India. Look at the type of disciplines that are involved. And many of them require advanced mathematics. Next slide. This is the Tsunami Early Warning Center. See, we had a tsunami in South India some time back. And since then, some years back, more than a decade back, and at that time, the Ministry of Environmental Sciences, see what happens is if you have an underground earthquake deep under the sea, and it's a magnitude above 7, the waves that it generates can cause the tsunami. So now, what they have done is to watch whether the seismic signal, that is mathematics. Source provides the seismic signal, and that comes over. Same thing with nuclear explosion. You want to measure the yield across the world. You must know what is the shock wave strength which is generated there, and of course you must also know the geology of the rock. All this they make use of. Usually we comparing with an earlier event on which they have the data, and it requires geoscience and mathematics. And UNESCO has designated this as a regional tsunami service provider for all countries in the Indian Ocean rim. Next slide. See, there are theory-driven experiments and experiments which lead to studies in theoretical studies. Looking for the Higgs boson is a theory-driven experiment. The weak force and electromagnetic force can be described in the same theory, which forms the basis of the standard model. Now, the unobserved particle was the Higgs boson I told you about, and this was observed in July 2012. Another example is the gravitational waves, predicted general theory of relativity, and finally detected in September 2015 by two detectors, LIGO, laser interferometry gravitational wave detectors. And that experiment had great contributions from two Indian scientists, Vishweshwara from RRI, Raman Research, and Sanjeev Dhurandhar. And now we are going to provide the third arm, because to locate the source of the gravitational waves, you need at least 3 detectors. And this work is going on. They have selected a site. Observatory will be jointly funded by the Department of Atomic Energy and the Department of Science and Technology. Next slide. Experiment-driven theory. Of course, the best example is superconductivity, observed in 1911, where they showed, Camerlengon showed that 4.2 degree Kelvin, the resistance abruptly disappeared in some material. And then the theory followed, Bardeen-Cooper-Schrieffer theory, named after John Bardeen, Leon Cooper, Robert Schrieffer. First microscopic theory of superconductivity. And then, of course, there are attempts now to achieve room temperature superconductivity. playing around with a variety of materials. And very recently, a new model for superconductivity has come up from Japan, University of Tsukuba. And there, instead of focusing on the pairing of charged particles, they use what is called the Berry connection, gives rise to a collective mode. Next slide. Artificial intelligence. Three branches of mathematics are used widely in artificial intelligence: linear algebra, calculus, and probability. Linear algebra, of course, you have application of AI, vectors, matrices, eigenvalues, eigenvectors. Calculus, functions, vector, matrix calculus. Probability, mainly they use a theorem called the Bayes theorem. The next step of the robot, which has already executed one step out. And other areas that may be needed: information Markov chain for stochastic processors used for reinforcement learning as compared to supervised machine learning. That is, as it goes on, the learning gets reinforced. Next slide. Because neuroscience, there is interest in math science, I know, in neuroscience. Artificial neural networks are based on neuroscience, deep learning. They are analogous to the synaptic connections between neurons in the brain. They are like a massively parallel distributed processor made up of simpler processing unit, artificial neurons. Resembles the brain in two respects: knowledge acquired by learning process, and then this knowledge is stored and, of course, recovered when needed. Now in reverse, neuroscientists are beginning to benefit from the power of AI, both as a model for developing and testing new ideas, how the brain involves computations and other aspects of cognitive science, and as a tool for processing complex data sets. Next slide. How will the future, what is the future of artificial intelligence? There are some scientists who are scared of course, the artificial intelligence, machine learning are used everywhere, from commerce and drug design to nuclear power expert systems. And AI is also designing expert systems that are based on AI. Nuclear power plant control, flood control in Chennai, done by a group in IIT Bombay. Well, the talk is now on how to reduce the human-machine divide. And there are people, as I said, who are scared of long-term development. The great astrophysicist who passed away some time back, Professor Stephen Hawking, once told, BBC correspondent, development of full artificial intelligence could spell the end of the human race. I do not agree with that. Agree more with Roger Penrose, who argues that using Gödel's incompleteness theorem in the context of AI, he comes to the conclusion that humans will always be smarter than computers and computer algorithms and any other cybernetic machines that they create. I agree. There is a wonderful book, all of you would have read it, The Man Who Knew Infinity, biography of Srinivasa Ramanujan. And while reviewing this book, Ezekiel Rohr at the Hebrew University of Jerusalem says, no enhancement of human intelligence opens a door to becoming a Ramanujan, and no algorithm is likely to produce robots with the abilities of Ramanujan. Next slide. The great Srinivasa Ramanujan, so-called magical genius, and K. Srinivasa Rao, I think he was associated with math science earlier, written a new book, Srinivasa Ramanujan, Life and Work of a Natural Mathematical Genius. And I picked some part from that. The natural mathematical genius born in an orthodox Iyengar family is an enigma, like the Big Bang. And he calls him a Swayambhu. He left behind notebooks containing 4,000 theorems which set the Cambridge mathematician just hardly wonder with awe and admiration. But there were no mistakes at all, or hardly any mistakes, I'll say. Some people tell me there were a few mistakes. I'm not very sure. It's not in the field. The fact that Ramanujan knew but did not write down the proofs of all his theorems, it seems like George Andrews says, a boon to generations of great mathematicians. Thanks to that, they said so many people have done excellent work in mathematics. And he didn't know it, but now Ramanujan's work is used in cryptography and coding theory, and somebody told me even in hotel booking. As Nobel laureate Chandrasekhar said, as long as people do mathematics, work of Ramanujan will continue to be appreciated, and I'm sure more and more applications of his work will continue to be found. Next slide. Take, of course, cybersecurity. Go back to the previous slide. As I mentioned here, Ramanujan's work finds applications in cryptography. Next slide. See, defending the internet is a difficult exercise, and to prevent and model, even if when security breaches have happened, all the cyber security tools and algorithms are based on mathematical ideas. Cryptography, encryption is based on mathematical theory, and one of the very important ones is the random number generation. And here is where the question of quantum computers comes up. If and when they come, maybe after a decade or so, instead of just binary 0 and 1, you can use any number of qubits. If and when it comes, it will be so powerful it can break any conventional RSA code. That's why a lot of people, including sets which Professor Valstronium mentioned, are working on post-quantum cryptography once a computer comes. And if you develop the keys which can be used based on quantum computers, then rest is by normal optical fiber transmission. Keys alone, then it will become almost unbreakable. Next slide. Of course, there are other areas of mathematical statistics. Great Mahalanobis, which is the application of probability theory, is taken from an address in the Indian Statistical Institute when was the 120th birth anniversary of Professor Mahalanobis. He was a pioneer in the field of statistical science. And his model of economic development and the concept of socio-economic planning has become the underlying framework for India's second five-year plan. See, that is because of him, India large-scale economic sample surveys carry credibility today. Many of the leading statistical scientists from India have had their careers, Lexia Rao, careers in Indian Statistical Institute. Next slide. Of course, it's not just in here, physical sciences, but take economics, for instance. Game theory is a theory based on mathematics, widely recognized. In fact, American mathematician John Nash was awarded the '94 Nobel Prize for Economics for his landmark work on the mathematics of game theory. And it is really the study of strategic interactions among rational decision makers. It is concerned with situations where decisions interact, where the payoff for a decision maker depends not only on his own decision, his or her own, but also on the decisions of others. Suppose I fix the price of a product, your decision, but the sale will depend upon the prices your competitors fix. And very interestingly, I noticed that so far Nobel Memorial Prize in Economics has been won by 11 game theories so far. It's a wonderful book written by Professor Y. Narahari. Gave me a copy of that. Game theory and mechanism design. Mechanism design is the converse of game theory. Of course, this is all theoretical. Game theory gives rise to theoretical predictions. But as the Nobel laureate Abhijit Banerjee and his wife say, that the lack of empirical evidence to back theoretical predictions has affected the credibility of economists. And interestingly, this recent Nobel Prize in Economics, announced a few days back, has been given to a trio for their work in empirical economics. Next slide. We come to the end now. Great Bhabha, who founder of the Atomic Energy Program, was a renowned theoretical and high energy physicist in Cambridge, and pioneering work there on cosmic ray showers and electron-positron scattering, now known as Bhabha scattering. And there are two kinds of leaders, which Arthur Koestler calls the yogi and the commissar. Yogi is the contemplative thinker. Commissar is the man of action. And Bhabha was a unique mixture of both. And the most important thing is he created a leadership swarm around him. Setna, Ramana, Brahmaprakash, S. Rao, all those people carried on the program, even though he passed away tragically at the early age of 56 years. And thanks to this leadership swarm, the atomic energy program has continued to flourish. Bhabha had, of course, technology foresight. Thinking of making nuclear reactors at a time when there were not even indigenous bicycle designs. But he also had a grand vision for science. And he created the Tata Institute of Fundamental Research. And he realized the importance of mathematics. Now, that is why mathematics has flourished in India because of the Department of Atomic Energy. Starting with TFR, now we also have institutions like IMSc, Harish Chandra Institute, which is under DAE. They are leaders in the country. And DAE also supports mathematics through National Board of Higher Mathematics. Next slide, which is my last slide. Let me come back to the quotation. And it's what I've tried to convey when I was talking about India's achievements, science and technology, this being a Amrit Mahotsav year, 75th year of our independence, by the famous physicist, Nobel Prize winner in particle physics, Eugene Paul Wigner, who says, language of mathematics reveals itself not just effective in the natural, unreasonably effective. That's a very interesting additional word that he has used there, that it is so important and it gives you results which you may not have anticipated in the beginning. Next slide. Thank you very much. Thank you. I think my lectures. Thanks a lot.
Thank you. Thank you very much, Dr. Chidambaram, for this very interesting talk. We made so many different points on the diverse roles of mathematics and its connections to physics and physical sciences, economics. It was quite illuminating. Thank you very much.
Thank you.